start with a bit of a personal question. Am I an AI program you wrote to interview people until I get good enough to interview you?
Well, I'd be impressed if you were. I'd be impressed with myself if you were. I don't think we're quite up to that yet, but maybe you're from the future, Lex.
If you did, would you tell me? Is that a good thing to tell a language model that's tasked with interviewing that it is in fact AI?
Maybe we're in a kind of meta Turing test. Probably it would be a good idea not to tell you, so it doesn't change your behavior, right?
This is a kind of
Heisenberg uncertainty principle situation. If I told you, you'd behave differently.
Yeah.
Maybe that's what's happening with us, of course.
This is a benchmark from the future where they replay 2022 as a year before AIs were good enough yet, and now we want to see, is it going to pass?
Exactly.
If I was such a program, would you be able to tell, do you think? So to the Turing test question, you've talked about the benchmark for solving intelligence. What would be the impressive thing? You talked about winning a Nobel Prize, an AI system winning a Nobel Prize, but I still return to the Turing test as a compelling test, the spirit of the Turing test as a compelling test.
Yeah, the Turing test, of course, it's been unbelievably influential, and Turing's one of my all-time heroes. But I think if you look back at the 1950 paper, his original paper, and read the original, you'll see I don't think he meant it to be a rigorous formal test. I think it was more like a thought experiment, almost a bit of philosophy he was writing, if you look at the style of the paper. And you can see he didn't specify it very rigorously. So, for example, he didn't specify the knowledge that the expert or judge would have. Not, how much time would they have to investigate this? So these are important parameters if you were going to make it a true sort of formal test. And, by some measures, people claim the Turing test passed several, a decade ago. I remember someone claiming that with a kind of very bog standard normal logic model because they pretended it was a kid. So the judges thought that the machine, was a child. So that would be very different from an expert AI person interrogating a machine and knowing how it was built and so on. So I think we should probably move away from that as a formal test and move more towards a general test where we test the AI capabilities on a range of tasks and see if it reaches human level or above performance on maybe thousands, perhaps even millions of tasks eventually, and cover the entire sort of cognitive space. So I think for its time, it was an amazing thought experiment. And also 1950s, obviously, there's barely the dawn of the computer age. So, of course, he only thought about text. And now we have a lot more different inputs.
So, yeah, maybe the better thing to test is the generalizability, so across multiple tasks. But I think it's also possible, as systems like Gato show, that eventually that might map right back to language. So you might be able to demonstrate your ability to generalize across tasks by then communicating your ability to generalize across tasks, which is kind of what we do through conversation anyway, when we jump around. Ultimately, what's in there in that conversation is not just you moving around knowledge. It's you moving around like these entirely different modalities of understanding that ultimately map to your ability to operate successfully in all of these domains, which you can think of as tasks.
Yeah, I think certainly we as humans use language as our main generalization communication tool. So I think we end up thinking in language and expressing our solutions in language. So it's going to be a very powerful mode in which to explain, the system, to explain what it's doing. But I don't think it's the only modality that matters. So I think there's going to be a lot of, there's a lot of different ways to express capabilities other than just language.
Yeah, visual, robotics, body language, actions, the interactive aspect of all that. That's all part of it.
But what's interesting with Gato is that it's sort of pushing prediction to the maximum in terms of mapping arbitrary sequences to other sequences and sort of just predicting what's going to happen next. So prediction seems to be fundamental to intelligence.
And what you're predicting doesn't so much matter.
Yeah, it seems like you can generalize that quite well. So obviously language models predict the next word. Gato predicts potentially any action or any token. And it's just the beginning, really. It's our most general agent, one could call it, so far. But that itself can be scaled up massively more than we've done so far, and obviously we're in the middle of doing that.
But the big part of solving AGI is creating benchmarks that help us get closer and closer, sort of creating benchmarks that test the generalizability. And it's just still interesting that this fella, Alan Turing, was one of the first and probably still one of the only people that was trying, maybe philosophically, but was trying to formulate a benchmark that could be followed. It is, even though it's fuzzy, it's still sufficiently rigorous to where you can run that test. And I still think something like the Turing test will, at the end of the day, be the thing that truly impresses other humans, so that you can have a close friend who's an AI system. And for that friend to be a good friend, they're going to have to be able to play StarCraft, and they're going to have to do all of these tasks. Get you a beer, so the robotics tasks, play games with you, use language, humor, all of those kinds of things. But that ultimately can boil down to language. It feels like not in terms of the AI community, but in terms of the actual impact of general intelligence on the world, it feels like language will be the place where it truly shines.
I think so, because it's such an important kind of input output for us. I think you're right. I think the Turing test, that what the kind of the philosophy behind it, which is the idea of can a machine mimic the behaviors of a human, and I would say wider than just language and text. Then, in terms of actions and everything else, creativity, all these things, then if it can sort of match or exceed human cognitive capabilities, then I think we have a true intelligence. So from that perspective, you're right. I think he did formulate the right kind of setup.
I think there'll be a kind of humor in the AI systems of the future, looking back to this conversation and thinking about the Turing test, and also thinking about, by that time they would know which year they were finally able to sort of cross the threshold of human level intelligence, and think how funny it is that we humans were still confused about this whole problem that's been long ago been solved. Well, hello to the AI agents of the future. Anyway, so going back to your journey, when did you fall in love with programming first?
Well, it was pretty young age, actually. So, I started off, actually games was my first love. So starting to play chess when I was around 4 years old. And then it was actually with winnings from a chess competition that I managed to buy my first chess computer when I was about 8 years old. It was a ZX Spectrum, which was hugely popular in the UK at the time. And it was an amazing machine, because I think it trained a whole generation of programmers in the UK, because it was so accessible. You literally switched it on and there was the basic prompt and you could just get going. And my parents didn't really know anything about computers, but because it was my money from a chess competition, I could say I wanted to buy it. And then I just went to bookstores, got books on programming, and started typing in the programming code, and then of course once you start doing that, you start adjusting it and then making your own games. And that's when I fell in love with computers and realized that they were a very magical device. In a way, I wouldn't have been able to explain this at the time, but I felt that they were sort of almost a magical extension of your mind. I always had this feeling, and I've always loved this about computers, that you can set them off doing something, some task for you. You can go to sleep, come back the next day, and it's solved. That feels magical to me. So, I mean, all machines do that to some extent. They all enhance our natural capabilities. Obviously, cars allow us to move faster than we can run. But this was a machine to extend the mind. And then, of course, AI is the ultimate expression of what a machine may be able to do or learn. So very naturally for me, that thought extended into AI quite quickly.
Do you remember the programming language that was first started in?
Yeah.
Was it special to the machine, or was
it was just a base. It was just I think it was just basic on the ZX Spectrum. I don't know what specific form it was. And then later on, I got a Commodore Amiga, which
nice.
Was a fantastic machine.
Now you're just showing off.
So yeah, well, lots of my friends had Atari STs, and I managed to get Amigas. It was a bit more powerful, and that was incredible. And used to do programming in assembler and also Amos Basic, this specific form of Basic. It was incredible, actually, as well as all my coding skills.
And when did you fall in love with AI? So when did you first start to gain an understanding that you can not just write programs that do some mathematical operations for you while you sleep, but something that's akin to bringing an entity to life, sort of a thing that can figure out something more complicated than a simple mathematical operation.
Yeah, so there was a few stages for me all while I was very young. So first of all, as I was trying to improve at playing chess, so I was captaining various England junior chess teams. And at the time, when I was about, maybe 10, 11 years old, I was going to become a professional chess player. That was my first thought.
So that dream was there to
sure
try to get to the highest levels of chess.
So I was, I got to, when I was about 12 years old, I got to master standard, and I was second highest rated player in the world to Judith Polgar, who obviously ended up being an amazing chess player and world women's champion. And when I was trying to improve at chess, well, what you do is you obviously, first of all, you're trying to improve your own thinking processes. So that leads you to thinking about thinking. How is your brain coming up with these ideas? Why is it making mistakes? How can you improve that thought process? But the second thing is that it was just the beginning. This was like in the early 80s, mid 80s of chess computers. If you remember, they were physical boards like the one we have in front of us, and you press down the squares. And I think Kasparov had a branded version of it that I got. And you used to, they're not as strong as they are today, but they were pretty strong, and you used to practice against them to try and improve your openings and other things. And so I remember, I think I probably got my first one, I was around 11 or 12. And I remember thinking, this is amazing. How has someone programmed this chessboard to play chess? And it was a very formative book I bought, which was called The Chess Computer Handbook by David Levy. It came out in 1984 or something. So I must have got it when I was about 11, 12. And it explained fully how these chess programs were made. And I remember my first AI program being programming my Amiga. It wasn't powerful enough to play chess. I couldn't write a whole chess program, but I wrote a program for it to play Othello. Or Reversi, it's sometimes called, I think, in the US. And so a slightly simpler game than chess, but I used all of the principles that chess programs had, alpha, beta search, all of that. And that was my first AI program. I remember that very well. I was around 12 years old. So that brought me into AI. And then the second part was later on when I was around 16, 17, and I was writing games professionally, designing games, writing a game called Theme Park, which had AI as a core gameplay component as part of the simulation. And it sold, millions of copies around the world, and people loved the way that the AI, even though it was relatively simple by today's AI standards, was reacting to the way you as the player played it. So it was called a sandbox game. So it was one of the first types of games like that, along with SimCity. And it meant that every game you played was unique.
Is there something you could say, just on a small tangent, about really impressive AI from a game design, human enjoyment perspective? Really impressive AI that you've seen in games, and maybe what does it take to create an AI system, and how hard of a problem is that? So a million questions would just as a brief tangent.
Well, look, I think games have been significant in my life for three reasons. So first of all, I was playing them and training myself on games when I was a kid. Then I went through a phase of designing games and writing AI for games. So all the games I professionally wrote had AI as a core component, and that was mostly in the 90s. And the reason I was doing that in games industry was, at the time, the games industry, I think, was the cutting edge of technology. So whether it was graphics with people like John Carmack and Quake and those kind of things, or AI, I think actually all the action was going on in games. And we're still reaping the benefits of that, even with things like GPUs, which I find ironic, was obviously invented for graphics, computer graphics, but then turns out to be amazingly useful for AI. It just turns out everything's a matrix multiplication. It appears, in the whole world.
Yes.
So I think games at the time had the most cutting edge AI, and a lot of the games I was involved in writing. So there was a game called Black and White, which was one game I was involved with in the early stages of, which I still think is the most impressive example of reinforcement learning in a computer game. So in that game, you trained a little pet animal, and
it's a brilliant game.
Yeah, and it sort of learned from how you were treating it. So if you treated it badly, then it became mean, and then it would be mean to your villagers and your population, the sort of the little tribe that you were running. But if you were kind to it, then it would be kind. And people were fascinated by how that was. And so was I, to be honest, with the way it kind of developed. And
especially the mapping to good and evil.
Yeah.
It made me realize that you can sort of in the choices you make can define the where you end up, and that means all of us are capable of the good, evil. It all matters in the different choices along the trajectory to those places that you make. It's fascinating. I mean, games can do that philosophically to you, and it's rare. It seems rare.
Yeah, well, games are, I think, a unique medium because you, as the player, you're not just passively consuming the entertainment, right? You're actually actively involved as an agent. So I think that's what makes it, in some ways, can be more visceral than other mediums like films and books. So that was designing AI in games, and then the third use we've used of AI is in DeepMind from the beginning, which is using games as a testing ground for proving out AI algorithms and developing AI algorithms. And that was a sort of a core component of our vision at the start of DeepMind, was that we would use games very heavily as our main testing ground, certainly to begin with, because it's super efficient to use games, and also it's very easy to have metrics to see how well your systems are improving and what direction your ideas are going in and whether you're making incremental improvements.
And because those games are often rooted in something that humans did for a long time beforehand, there's already a strong set of rules. Like, it's already a damn good benchmark.
Yes, it's really good for so many reasons, because you've got clear measures of how good humans can be at these things.
That's right.
And in some cases, like Go, we've been playing it for thousands of years.
Yeah.
And often they have scores or at least win conditions. So it's very easy for reward learning systems to get a reward. It's very easy to specify what that reward is. And also at the end, it's easy to test externally, at how strong is your system by, of course, playing against the world's strongest players at those games. So it's so good for so many reasons, and it's also very efficient to run potentially millions of simulations in parallel on the cloud. So I think there's a huge reason why we were so successful back in starting out 2010. How come we were able to progress so quickly? Because we'd utilize games, and at the beginning of DeepMind, we also hired some amazing game engineers who I knew from my previous lives in the games industry, and that helped to bootstrap us very quickly.
And plus, it's somehow super compelling, almost at a philosophical level, of man versus machine over a chessboard or a Go board. And especially given that the entire history of AI is defined by people saying it's going to be impossible to make a machine that beats a human being in chess. Yeah. And then once that happened, people were certain, when I was coming up in AI, that Go is not a game that could be solved because of the combinatorial complexity. It's just it's no matter how much Moore's law you have, compute is just never going to be able to crack the game of Go.
Yeah.
And so then there's something compelling about sort of taking on the impossibility of that task from the AI researcher perspective, engineer perspective, and then as a human being, just observing this whole thing. Your beliefs about what you thought was impossible being broken apart. It's humbling to realize we're not as smart as we thought. It's humbling to realize that the things we think are impossible now perhaps will be done in the future. There's something really powerful about a game, AI system beating a human being in a game, that drives that message home for like billions of people, especially in the case of Go.
Sure. Well, look, I think it has been a fascinating journey, and especially as I think about it I can understand it from both sides, both as the AI, creators of the AI, but also as a games player originally. Yeah. So, it was a really interesting, it was a fantastic, but also somewhat bittersweet moment, the AlphaGo match for me, seeing that and being obviously heavily involved in that. But, as you say, chess has been Kasparov, I think, rightly called it the Drosophila of intelligence, right? So it's sort of, I love that phrase. And I think he's right, because chess has been hand in hand with AI from the beginning of the whole field, right? So I think every AI practitioner, starting with Turing and Claude Shannon and all those, the sort of forefathers of the field, tried their hand at writing a chess program. I've got original edition of Claude Shannon's first chess program. I think it was 1949, the original sort of paper. And they all did that. And Turing famously wrote a chess program but all the computers around then were obviously too slow to run it. So he had to be the computer, right? So he literally, I think, spent 2 or 3 days running his own program by hand with pencil and paper and playing a friend of his with his chess program. So, of course, Deep Blue was a huge moment, beating Kasparov. But actually, when that happened, I remember that very, very vividly, of course, because it was, chess and computers and AI, all the things I loved. And I was at college at the time. But I remember coming away from that being more impressed by Kasparov's mind than I was by Deep Blue, because here was Kasparov with his human mind. Not only could he play chess more or less to the same level as this brute of a calculation machine, but of course, Kasparov can do everything else humans can do: ride a bike, talk many languages, do politics, all the rest of the amazing things that Kasparov does. And so with the same brain. And yet Deep Blue, brilliant as it was at chess, it'd been hand-coded for chess and actually had distilled the knowledge of chess grandmasters into a cool program, but it couldn't do anything else. Like it couldn't even play a strictly simpler game like tic-tac-toe. So something to me was missing from intelligence from that system that we would regard as intelligence. And I think it was this idea of generality and also learning. And that's obviously what we tried to do with AlphaGo.
Yeah, with AlphaGo and AlphaZero, MuZero, and then Gato, and all the things that we'll get into some parts of. There's just a fascinating trajectory here. But let's just stick on chess briefly. On the human side of chess, you've proposed that from a game design perspective, the thing that makes chess compelling as a game is that there's a creative tension between a bishop and the knight. Can you explain this? First of all, it's really interesting to think about what makes a game compelling, makes it stick across centuries.
Yeah, I was sort of thinking about this, and actually a lot of even amazing chess players don't think about it necessarily from a games designer point of view. So it's with my game design hat on that I was thinking about this. Why is chess so compelling? And I think a critical reason is the dynamicness of the different kind of chess positions you can have, whether they're closed or open and other things, comes from the bishop and the knight. So if you think about how different the capabilities of the bishop and knight are in terms of the way they move, and then somehow chess has evolved to balance those two capabilities more or less equally. So they're both roughly worth 3 points each.
So you think that dynamics was always there, and then the rest of the rules are kind of trying to stabilize the game?
Well, maybe. I mean, it's sort of, I don't know, it's chicken and egg situation. Probably both came together. But the fact that it's got to this beautiful equilibrium where you can have the bishop and knight that are so different in power, but so equal in value across the set of the universe of all positions, right? Somehow they've been balanced by humanity over hundreds of years. I think gives the game the creative tension that you can swap the bishop and knights for a bishop for a knight, and they're more or less worth the same. But now you aim for a different type of position. If you have the knight, you want a closed position. If you have the bishop, you want an open position. So I think that creates a lot of the creative tension in chess.
So some kind of controlled creative tension. From an AI perspective, do you think AI systems could eventually design games that are optimally compelling to humans?
Well, that's an interesting question. Sometimes I get asked about AI and creativity, and the way I answered that is relevant to that question, which is that I think there are different levels of creativity, one could say. So I think if we define creativity as coming up with something original, right, that's useful for a purpose, then I think the kind of lowest level of creativity is like an interpolation, so an averaging of all the examples you see. So maybe a very basic AI system could say you could have that. So you show it millions of pictures of cats, and then you say, give me an average looking cat, right? Yes. Generate me an average looking cat. I would call that interpolation. Then there's extrapolation, which something like AlphaGo showed. So AlphaGo played, millions of games of Go against itself. And then it came up with brilliant new ideas like Move 37 in game 2, brilliant motif strategies in Go that no humans had ever thought of, even though we've played it for thousands of years and professionally for hundreds of years. So that I call that extrapolation. But then there's still a level above that, which is, you could call out of the box thinking or true innovation, which is, could you invent Go? Right? Could you invent chess and not just come up with a brilliant chess move or brilliant Go move, but can you actually invent chess or something as good as chess or Go? And I think one day AI could, but what's missing is how would you even specify that task to a program right now? And the way I would do it if I was telling a human to do it or a games designer, a human games designer to do it, is I would say something like Go. I would say, come up with a game that only takes 5 minutes to learn, which Go does because it's got simple rules, but many lifetimes to master, right? Or impossible to master in one lifetime because it's so deep and so complex. And then it's aesthetically beautiful. And also it can be completed in 3 or 4 hours of gameplay time, which is, useful for us, in a human day. And so you might specify these sort of high level concepts like that. And then, with that and maybe a few other things, one could imagine that Go satisfies those constraints. But the problem is that we're not able to specify abstract notions like that, high-level abstract notions like that yet to our AI systems. And I think there's still something missing there in terms of high-level concepts or abstractions that they truly understand and combinable and compositional. So for the moment, I think AI is capable of doing interpolation and extrapolation, but not true invention.
So coming up with rule sets and optimizing with complicated objectives around those rule sets, we can't currently do. But you could take a specific rule set and then run a kind of self-play experiment to see how long, just observe how an AI system from scratch learns. How long is that journey of learning? And maybe if it satisfies some of those other things you mentioned in terms of quickness to learn and so on, and you could see a long journey to master for even an AI system, then you could say that this is a promising game. But it would be nice to do almost like AlphaGo, so programming rules. So generating rules that kind of that automate even that part of the generation of rules.
So I have thought about systems actually that I think would be amazing in for a games designer if you could have a system that takes your game, plays it tens of millions of times, maybe overnight, and then self-balances the rules better. So it tweaks the rules and maybe the equations and the parameters so that the game is more balanced, the units in the game or some of the rules could be tweaked. So it's a bit of like giving it a base set and then allowing Monte Carlo tree search or something like that to sort of explore it, right? And I think that would be super a powerful tool actually for balancing, auto-balancing a game, which usually takes thousands of hours from hundreds of human games testers normally to balance one game like StarCraft, which is Blizzard are amazing at balancing their games, but it takes them years and years and years. So one could imagine at some point when this stuff becomes efficient enough to you might be able to do that like overnight.
Do you think a game that is optimal, designed by an AI system, would look very much like Planet Earth?
Maybe certainly the sort of game I would love to make is, and I've tried, in my games career, the games design career, my first big game was designing a theme park, an amusement park. Then with games like Republic, I tried to have games where we designed whole cities and allowed you to play in. So, and of course, people like Will Wright have written games like Sim Earth, trying to simulate the whole of Earth. Pretty tricky, but
Sim Earth, I haven't actually played that one. So, what is it? Does it incorporate evolution or?
Yeah, it has evolution, and it's sort of it tries to it sort of treats it as an entire biosphere, but from quite high level. So
it'd be nice to be able to sort of zoom out, and zoom in.
Exactly. So obviously, it couldn't do that. Was in the night. I think he wrote that in the 90s, so it couldn't. It wasn't able to do that. But that would be obviously the ultimate sandbox game, of course.
On that topic, do you think we're living in a simulation?
Yes. Well, so okay. So
we're going to jump around from the absurdly philosophical to the technical.
Sure. Very, very happy to. So I think my answer to that question is a little bit complex because there is simulation theory, which obviously Nick Bostrom, I think, famously first proposed. And I don't quite believe it in that sense. So in the sense that are we in some sort of computer game, or have our descendants somehow recreated Earth in the 21st century and for some kind of experimental reason? I think that, but I do think that the best way to understand physics and the universe is from a computational perspective. So understanding it as an information universe, and actually information being the most fundamental unit of reality rather than matter or energy. So a physicist would say, matter or energy, E equals mc squared. These are the things that are the fundamentals of the universe. I'd actually say information, which of course itself can specify energy or matter, right? Matter is actually just, we're just out the way our bodies and the molecules in our body are arranged as information. So I think information may be the most fundamental way to describe the universe, and therefore you could say we're in some sort of simulation because of that. But I'm not really a subscriber to the idea that these are sort of throwaway billions of simulations around. I think this is actually very critical and possibly unique, this simulation.
This particular one.
Yes.
So, and you just mean treating the universe as a computer that's processing and modifying information is a good way to solve the problems of physics, of chemistry, of biology, and perhaps of humanity and so on.
Yes, I think understanding physics in terms of information theory might be the best way to really understand what's going on here.
From our understanding of a universal Turing machine, from our understanding of a computer, do you think there's something outside of the capabilities of a computer that is present in our universe? You have a disagreement with Roger Penrose about the nature of consciousness. He thinks that consciousness is more than just a computation. Do you think all of it, the whole shebang, can be a computation?
Yeah, I've had many fascinating debates with Sir Roger Penrose, and obviously he's famously, and I read Emperors of the New Mind and his books, his classical books, and they were pretty influential in the in the 90s, and he believes that there's something more, something quantum that is needed to explain consciousness and the brain. I think about what we're doing actually at DeepMind, and what my career is being, we're almost like Turing's champion. So we are pushing Turing machines or classical computation to the limits. What are the limits of what classical computing can do? Now, and at the same time, I've also studied neuroscience to see, and that's why I did my PhD in, was to see, also to look at, is there anything quantum in the brain from a neuroscience or biological perspective? And so far, I think most neuroscientists and most mainstream biologists and neuroscientists would say there's no evidence of any quantum systems or effects in the brain. As far as we can see, it can be mostly explained by classical theories. So so there's sort of the search from the biology side, and then at the same time there's the raising of the water at the bar from what classical Turing machines can do, and including our new AI systems. And as you alluded to earlier, I think AI, especially in the last decade plus, has been a continual story now of surprising events and surprising successes, knocking over one theory after another of what was thought to be impossible, from Go to protein folding and so on. And so I think I would be very hesitant to bet against how far the universal Turing machine and classical computation paradigm can go. And my betting would be that all of certainly what's going on in our brain can probably be mimicked or approximated on a classical machine, not requiring something metaphysical or quantum.
And we'll get there with some of the work with AlphaFold, which I think begins the journey of modeling this beautiful and complex world of biology. So you think all the magic of the human mind comes from this, just a few pounds of mush, of biological computational mush that's akin to some of the neural networks, not directly, but in spirit, that DeepMind has been working with?
Well, look, I think it's, you say it's a few, of course, this is I think the biggest miracle of the universe is that it is just a few pounds of mush in our skulls,
Yeah.
and yet it's also our brains are the most complex objects that we know of in the universe. So there's something profoundly beautiful and amazing about our brains, and I think that it's an incredibly efficient machine, and it's phenomenon basically. And I think that building AI, one of the reasons I want to build AI, and I've always wanted to, is I think by building an intelligent artifact like AI and then comparing it to the human mind, that will help us unlock the uniqueness and the true secrets of the mind that we've always wondered about since the dawn of history, like consciousness, dreaming, creativity, emotions. What are all these things, right? We've wondered about them since the dawn of humanity. And I think one of the reasons, and I love philosophy and philosophy of mind, is we found it difficult is there haven't been the tools for us to really, other than introspection, from very clever people in history, very clever philosophers, to really investigate this scientifically. But now suddenly we have a plethora of tools. Firstly, we have all of the neuroscience tools, fMRI machines, single cell recording, all of this stuff. But we also have the ability, computers and AI, to build intelligent systems. So I think that I think it is amazing what the human mind does, and I'm kind of in awe of it, really. And I think it's amazing that with our human minds, we're able to build things like computers and actually even think and investigate about these questions. I think that's also a testament to the human mind.
Yeah, the universe built the human mind that now is building computers that help us understand both the universe and our own human mind.
That's right. That's exactly it. I mean, I think that's one could say we're the mechanism by which the universe is going to try and understand itself.
Yeah. It's beautiful. So let's go to the basic building blocks of biology that I think is another angle at which you can start to understand the human mind, the human body, which is quite fascinating, which is from the basic building blocks, start to simulate, start to model how from those building blocks you can construct bigger and bigger, more complex systems, maybe one day the entirety of the human biology. So here's another problem that thought to be impossible to solve, which is protein folding. And AlphaFold, or specific AlphaFold 2, did just that. It solved protein folding. I think it's one of the biggest breakthroughs, certainly in the history of structural biology, but in general in science. Maybe from a high level, what is it and how does it work? Mm-hmm. And then we can ask some fascinating questions after.
Sure. So maybe to explain it to people not familiar with protein folding is, I first of all explain proteins, which is, proteins are essential to all life. Every function in your body depends on proteins. Sometimes they're called the workhorses of biology. And if you look into them, and I've, obviously as part of AlphaFold, I've been researching proteins and structural biology for the last few years. They're amazing little bio-nano machines, proteins. They're incredible if you actually watch little videos of how they work, animations of how they work. And proteins are specified by their genetic sequence, called their amino acid sequence. So you can think of it as their genetic makeup. And then in the body, in nature, they fold up into a 3D structure. So you can think of it as a string of beads, and then they fold up into a ball. Now, the key thing is you want to know what that 3D structure is, because the 3D structure of a protein is what helps to determine what does it do, the function it does in your body. And also, if you're interested in drugs or disease, you need to understand that 3D structure, because if you want to target something with a drug compound about to block something the protein's doing, you need to understand where it's going to bind on the surface of the protein. So obviously, in order to do that, you need to understand the 3D structure.
So the structure is mapped to the function.
The structure is mapped to the function, and the structure is obviously somehow specified by the amino acid sequence. And that's in essence the protein folding problem is, can you just from the amino acid sequence, the one-dimensional string of letters, can you immediately computationally predict the 3D structure?
Right. And
this has been a grand challenge in biology for over 50 years. So I think it was first articulated by Christian Anfinsen, a Nobel Prize winner in 1972, as part of his Nobel Prize winning beginning lecture, and he just speculated this should be possible to go from the amino acid sequence to the 3D structure, but he didn't say how. So it's been described to me as equivalent to Fermat's last theorem, but for biology. Right?
You should, as somebody that very well might win the Nobel Prize in the future, but outside of that, you should do more of that kind of thing. In the margins, just put random things that will take like 200 years to solve.
Set people off for 200 years.
It should be possible.
Exactly.
And just don't give any details.
Exactly. I think everyone should be. I'll have to remember that for future. So he set off, with this one throwaway remark, just like Fermat, he set off this whole 50-year field really of computational biology. And they had, they got stuck. They hadn't really got very far with doing this. And until AlphaFold came along, this is done experimentally, right? Very painstakingly. So the rule of thumb is, and you have to crystallize the protein, which is really difficult. Some proteins can't be crystallized, like membrane proteins. And then you have to use very expensive electron microscopes or X-ray crystallography machines. Really painstaking work to get the 3D structure and visualize the 3D structure. So the rule of thumb in experimental biology is that it takes one PhD student, their entire PhD, to do one protein. And with AlphaFold 2, we were able to predict the 3D structure in a matter of seconds. And so we were, over Christmas, we did the whole human proteome, or every protein in the human body, all 20,000 proteins. So the human proteome is like the equivalent of the human genome, but on protein space, and sort of revolutionized really what structural biologists can do, because now they don't have to worry about these painstaking experimentals. Should they put all of that effort in or not? They can almost just look up the structure of their proteins like a Google search.
And so there's a data set on which it's trained and how to map this amino acid sequence. First of all, it's incredible that a protein, this little chemical computer, is able to do that computation itself in some kind of distributed way and do it very quickly. Mm-hmm. That's a weird thing. And they evolved that way because, in the beginning, that's a great invention, just the protein itself of Earth. And then there's, I think, probably a history of they evolved to have many of these proteins, and those proteins figure out how to be computers themselves in such a way that you can create structures that can interact in complex ways with each other in order to form high-level functions. It's a weird system that they figured it out.
Well, for sure. Maybe we should talk about the origins of life too, but proteins themselves, I think, are magical and incredible. As I said, little bio nanomachines, and actually Leventhal, who is another scientist, a contemporary of Amundsen, he coined this what became known as Leventhal's paradox, which is exactly what you're saying. He calculated roughly an average protein, which is maybe 2,000 amino acids bases long, can fold in maybe 10 to the power 300 different conformations. So there's 10 to the power 300 different ways that protein could fold up, and yet somehow in nature, physics solves this in a matter of milliseconds. So proteins fold up in your body in, sometimes in fractions of a second. Mm-hmm. So physics is somehow solving that search problem.
And just to be clear, in many of these cases, maybe you can correct me if I'm wrong, there's often a unique way for that sequence to form itself.
Yes.
So among that huge number of possibilities, it figures out a way how to stably in some cases, there might be a misfunction, so on, which leads to a lot of the disorders and stuff like that. But most of the time, it's a unique mapping, and that unique mapping is not obvious.
No, exactly.
Which is what the problem is.
No, exactly. So there's a unique mapping usually if it's healthy, and as you say, in disease. So, for example, Alzheimer's, one conjecture is that it's because of a misfolded protein, a protein that folds in the wrong way, amyloid beta protein. So, and then because it folds in the wrong way, it gets tangled up, right, in your neurons. So, it's super important to understand both healthy functioning and also disease, is to understand what these things are doing and how they're structuring. Of course, the next step is sometimes proteins change shape when they interact with something. So they're not just static necessarily in biology.
Maybe you can give some interesting, sort of beautiful things to you about these early days of AlphaFold, of solving this problem, because unlike games, this is real physical systems that are less amenable to self-play type of mechanisms.
Sure.
Right? The size of the data set is smaller than you might otherwise like, so you have to be very clever about certain things. Is there something you could speak to? What was very hard to solve, and what are some beautiful aspects about the solution?
Yeah, I would say AlphaFold is the most complex and also probably most meaningful system we've built so far. So it's been an amazing time actually in the last 2-3 years to see that come through, because as we talked about earlier, games is what we started on, building things like AlphaGo and AlphaZero. But really the ultimate goal was to not just to crack games, it was just to use them to bootstrap general learning systems we could then apply to real world challenges. Specifically, my passion is scientific challenges like protein folding. And then AlphaFold, of course, is our first big proof point of that. And so in terms of the data and the amount of innovations that had to go into it, it was like more than 30 different component algorithms needed to be put together to crack the protein folding. I think some of the big innovations were that kind of building in some hard-coded constraints around physics and evolutionary biology to constrain sort of things like the bond angles in the protein and things like that. But not to impact the learning system. So still allowing the system to be able to learn the physics itself from the examples that we had. And the examples, as you say, there are only about 150,000 proteins. Even after 40 years of experimental biology, only around 150,000 proteins the structures have been found out about. So that was our training set, which is much less than normally we would like to use, but using various tricks, things like self-distillation. So actually using AlphaFold predictions, some of the best predictions that it thought was highly confident in, we put them back into the training set, right, to make the training set bigger. That was critical to AlphaFold working. So there was actually a huge number of different innovations like that were required to ultimately crack the problem. AlphaFold 1, what it produced was a distogram, so a kind of a matrix of the pairwise distances between all of the molecules in the protein, and then there had to be a separate optimization process to create the 3D structure. And what we did for AlphaFold 2 is make it truly end to end. So we went straight from the amino acid sequence of bases to the 3D structure directly without going through this intermediate step. And in machine learning, what we've always found is that the more end-to-end you can make it, the better the system. And it's probably because in the end, the system's better at learning what the constraints are than we are as the human designers of specifying it. So anytime you can let it flow end to end and actually just generate what it is you're really looking for, in this case, the 3D structure, you're better off than having this intermediate step, which you then have to handcraft the next step for. Mm-hmm. So it's better to let the gradients and the learning flow all the way through the system from the end point, the end output you want, to the inputs.
So that's a good way to start on a new problem. Handcraft a bunch of stuff, add a bunch of manual constraints with a small end-to-end learning piece, or a small learning piece, and grow that learning piece until it consumes the whole thing.
That's right. And so you can also see, this is a bit of a method we've developed over doing many sort of successful alpha, so we call them Alpha X projects, yeah. Right? The easiest way to see that is the evolution of AlphaGo to AlphaZero. So AlphaGo was a learning system, but it was specifically trained to only play Go. Right. So, and what we wanted to do with the first version of AlphaGo is just get to world champion performance, no matter how we did it. Right. And then of course, AlphaGo Zero, we removed the need to use human games as a starting point. Right. So it could just play against itself from random starting point from the beginning. So that removed the need for human knowledge about Go. And then finally, AlphaZero then generalized it so that any things we had in there, the system, including things like symmetry of the Go board, were removed. So that AlphaZero could play from scratch any two-player game. And then MuZero, which is our latest version of that set of things, was then extending it so that you didn't even have to give it the rules of the game. It would learn that for itself. So it could also deal with computer games as well as board games.
So that line of AlphaGo, AlphaGo Zero, AlphaZero, MuZero, that's the full trajectory of what you can take from imitation learning to full self-supervised learning.
Yeah, exactly. And learning the entire structure of the environment you're put in from scratch, right? And bootstrapping it through self-play yourself. But the thing is, it would have been impossible, I think, or very hard for us to build Alpha Zero or Mu Zero first out of the box.
Even psychologically, because